Yeah, so very good evening today. And today we are going to start with our next lecture, which is on the topic multiple linear regression. Multiple linear regression. Okay, right. So until now, we have worked with only one input column and one target column. Like we were using the example of CGPA, and my output column was the package the person has got. Okay, so now we are going to shift our focus when we have more than one input column. That is, we will shift our focus from one dimension, two dimension to two, three dimension now. Okay, so let's say now I have a third input column, which is the IQ level of a person. Okay, so now my this package is depending on two input variables, which is the IQ of a person and the CGPA he has got during his studies. Okay, so let's say until now the equation of my line was y equals to mx plus b, but now, since I have more than one x, that is the input, the equation of my line will change as y equals to b0 plus beta 1 x1 plus beta 2 x2. Okay, so what is this beta? It is the b intercept or y intercept. Okay, so b1 is m1, which is the weight of x1, which is determining y. Okay, so how much x is contributing in determining y is defined by b1, right? And this is my input one, and beta 2 is the m2 or the slope of my variable x2. That is how much y is determined by my x2, right? So in terms of this, like IQ and CGPA, I can rewrite this equation as y or LPA is equal to beta 0, which is my y-intercept, plus beta 1 and multiplied by IQ, right? Plus beta 2 into multiplied by my CGPA, right? Okay, so there might be a question like from where these B0, B1 and B2 are coming. So the similar it is similar to how we optimized our loss function in my previous videos, and by optimizing the loss function we were getting the values of b0 or the m slope and the intercept. Similarly, we will formulate this equation into a loss function through which we will get the best values of b1 b2 and b0, which will minimize my loss function, right? So in my two dimension, what was my loss function doing is it was trying to reduce these errors, right? Like, oh, what my model is predicting and what is the reality of that point, right? So my error I was optimizing to reduce those errors. Similarly, in a 3D plane, in a three dimension, my aim is to reduce these errors, but now I won't be getting a single line, but in a three dimension, there will be a plane like this, right? And I have to reduce these distances of error from my plane, right? So suppose I will formulate it like this. I have my IQ, CGPA, and placement, right? And this is my row one. This is my row two. For now, let's take two rows, and the IQ is 70, CGPA is 7, and he's getting a package of 7.5 lakhs. And like IQ is 80, CGPA is 8, and this person is getting a package of, let's say, 12 lakhs, right? And then there will be my predictions using the model and the values of B0, B1, and B2, which I will be getting. And making my plane, right? So when I pass this value of 70 and 7 in this equation of y hat equals to b0 plus beta 1 x1 plus beta 2 x2, I will get a prediction, and that prediction might be 8 LPA. This might be 10 LPA, right? So what is happening here is for row 1, my prediction is coming out like this: y1 equals to beta 0 plus beta 1. These betas will be same for all my rows, helping in predicting all my rows. But what will change is this x value. So this is x11 plus beta 2 x22, right? Um, where this value is representing, sorry, this will be x12. So this value is representing my nth row, and this second value is representing my column. So this is column 1. This 2 is representing column 2. Similarly, for y2 at, it will be b0 plus b1 x12 plus beta 2 x22. So it is the 21 plus 22, right? So this is 2 comma 2. This is second row, and this is 2 1. Sorry, I'm sorry for this. This is 2 1 and this is 2 2. This is the second row and first column, and this is the second row, second column, right? Okay, so now you will see here that we can extend this concept to n number of, or m number of terms, or m number of input columns, right? So I can write this as b3 and x second row and third column up to beta n x2 mth input column. This is my row, second row, and this is my input column m, right? And I can do this for n input columns. Okay, so this will be beta 0 plus beta 1 x nth row first column plus beta 2 x nth row second column dot plus beta n x nth row mth input column. So graphically, or visually, it is like this. I have my input column 1, input column 2, input column 3, up to n input columns, and one target all column, and these are my n number of rows. Okay, so now what we can do is write this whole thing in terms of a matrix, right? So what I will do is, uh, let me define RHS first, which is my output column, right? So these values will be y1 hat, y2 hat, up to yn hat. So these are the predictions or the predicted values. Okay. So this is my prediction matrix, right? Or the values that are predicted by my model. Okay, on the left side, I need two things, the betas and the x, for which I will dot product these and get these output values. Okay, let me explain this properly. So I have this x matrix where I have my x11, x12, up to x1n, x21, x22, up to x2. Sorry, this is m, my mth input column, right? This is my mth input column on the nth row. So similarly, I can do this for x nth row first column, x nth row second column, up to x nth row mth column, right? So the shape of this matrix will be n into n into m, right? Right. These are n number of columns and n number of rows and m number of input columns. And when I dot product it with beta 0, beta 1, beta 2, up to beta n. Okay, so I hope you have seen an error here. Okay, so what I need to do is add a one term here. This is a scalar value 1, and this will change the shape of my matrix as it will become n plus, sorry, this will become n rows into m plus 1 columns. And you will realize why I have done this, because the beta value is independent of these x input values. So I need to dot product it with 1. This will give me 1 into, okay, so we do matrix multiplication in this form, right? Rows into columns. So it will give me beta 0 plus x 1 into beta 1 plus x 2 into beta 2 up to x 1m into beta n, right? And this is the form which I needed. It is exactly same, which I am writing here, right? Yeah, x. Yeah, so for nth row, it will be nm, and for first row, it will be 1 into m, which is exactly what I have written here. So this is why I have to add 1 in this matrix, which is quite not intuitive, but it is written this way. And the shape of my beta matrix is of the, it is n plus 1 rows into 1 column, right? So when I do multiply these two matrices, I get my output matrix n into 1 of the shape n into 1. So this is how I have represented my the input and output features. Input features multiplied by the coefficients give me the output. So it is of the form x into beta equals to y hat. Okay. Yeah, so we have done till the part that my target matrix is formed by multiplying my input matrix with the coefficients, right? Coefficient and intercept, that forms the beta matrix. Okay, so now we know that the error, my error would be y minus y hat, right? So we have studied this part that if this is my regression line and these are my points here, so these distances form the error. That is, this point shows what my regression line is predicting, while this is the reality where this point exists, right? Corresponding to this x. So I need to minimize these errors. So we know that our loss function is y minus y hat whole square, the summation, right? This is the loss function which I need to minimize. And right now I have this error. So what does this error represent? First, we must know this, that this error term is a matrix, because it shows y minus y hat, which both are matrix by themselves, right? So this represents y1 minus y1 hat, y2 minus y2 hat up to yn minus yn hat. Okay. And I need to make it in this form, right? Y minus y hat whole square. So what do I do? I cannot just simply put a square here, right? So, um, okay. So if I multiply this E with E transpose, there will be an issue, that because this my E matrix is of the form uh, n multiplied by 1, right? N number of rows and 1 column, and E transpose would be of the form 1 into n. So it will give me a new matrix of n into n, and I don't want that. My error term would be a single scalar value, right? Because it shows the total summation of my errors in my model. So what I need to do is multiply E transpose with my E. Okay, so it will look like, it will be of the form 1 into n multiplied by n into 1. So this will give me an output of 1 multiplied by 1, right? It will be a scalar value, which is my error. total error of my model, right? And yeah, so my new loss function is this, which I need to minimize. It is E transpose E, which looks like y1 minus y1 hat, y2 minus y2 hat, up to yn minus yn hat, multiplied by y1 minus y1 hat, y2 minus y2 hat, up to yn minus yn hat. And you will notice that if we multiply these two matrices, it will be of the form y1 summation y1 minus y1 hat whole square plus y2 minus y2 hat whole square up to yn minus yn hat whole square. And we can write it as summation I equals to 1 up to n yi minus yi hat whole square. And see, this was the loss function where we started, and this is equals to E transpose E. Yeah. So we have got our error loss function, and we need to minimize this term to get my beta coefficients, will which will give me the coefficient and intercept, which will minimize my loss, right? But we must remember that we are not working here in a 3D plane and not a 2D plane, right? So I will be getting a plane here or a hyperplane in multi-dimensional when I have n dimensions, which we cannot visualize, right? We can visualize up to 3 dimensions. And these will be my errors. And I need to minimize these by differentiating this function with respect to beta and putting it equal to 0, right? So this is now what we will be doing. Okay. So my loss function is E transpose E, which is equals to yi minus yi hat. Okay, so I don't need to write this I term because it is a matrix in itself, and transpose multiplied by y minus y hat. Okay, and we know that y hat is equals to x times beta, x dot beta. It is a dot product of matrices, right? And now if I send this transpose inside, so A plus B whole transpose is equals to A transpose plus B transpose, right? So this will be Y transpose minus Y hat transpose. And this is multiplied by Y minus Y hat, right? And, and now if I replace this Y hat with X beta, it will be Y transpose minus X beta whole transpose multiplied by Y minus Y hat, right? And now if I send this transpose inside, so A, B transpose equals to B transpose, A transpose, right? It is the property of matrices. And so my Y transpose minus beta transpose, X transpose multiplied by Y minus X beta. Okay, so now if I multiply these both terms, this will be equal to Y transpose Y minus Y transpose X beta minus beta transpose X transpose Y plus beta transpose X transpose X beta. Okay, so now here we will notice that I have these two terms, and I will prove to you in the next session that these both terms are equal. That is, this matrix is a symmetric matrix, which will imply that if I transpose this, it will be equal to beta transpose X transpose Y. Okay, so I will prepare a video on this to prove that these both two are equal, and we will move forward with this with knowing that these two are equal. Okay, so I can write it as Y transpose Y minus 2 Y transpose X beta plus beta transpose x beta, and this is my loss function. And now I need to differentiate it with respect to beta and put it equal to 0, right? Okay, so let's go ahead. My dl by d beta will be equal to, so this term will become 0 because this is a constant. I have my output matrix in hand and this is a constant. uh, okay, so now for this term it will be minus 2 y transpose x, right? Okay, so now if we focus on this term, it is of the form x transpose a x, right? And here we will notice as x is a matrix. So to differentiate a matrix of this form, the output is equal to 2 times a x transpose. This is a rule of matrix differentiation, which you can search on Google. And the output is of this form where a is a constant and x is a matrix, right? So in this term, the our constant is this. This is a constant and beta is the matrix, right? A could be a matrix which is a constant matrix, which don't contain variable terms, but our beta contains variable terms which are which we are trying to set to minimize our loss function, right? So the the differentiation of this matrix with respect to beta will be 2 times this constant x transpose x and the transpose of beta transpose. Okay, and now if we put it equal to 0, I send one term to the RHS, then it will become 2x transpose x beta transpose is equal to 2 times y transpose x. And this 2 gets cancelled. And now I have beta transpose is equal to y transpose x, that is this term, multiplied by x transpose x inverse. Okay, so if I send it to the right side, I cannot write it as 1 upon x transpose x, but I can write it as x transpose x whole inverse. And now I hope you know that what is the inverse of a matrix, that is 1 upon determinant of A multiplied by its adjoint. Okay, so yeah, so if we calculate this inverse and we multiply it with this, we will get our beta transpose. Now I don't want my beta transpose, I want beta. So I will take the transpose of both these matrices, okay, on the LHS and RHS. So it will become beta transpose full transpose is equal to y transpose x multiplied by x transpose x mm, inverse transpose, right? Okay, so it is not whole transpose, whole inverse, sorry. It is inverse on X matrix, uh, X transpose X, right? So now my beta will become X transpose X inverse transpose multiplied by Y transpose X transpose, because A multiplied by B whole transpose is equal to B transpose A transpose, right? So I have applied this identity here. And now, yeah. So it will become beta is equal to X transpose X inverse multiplied by X transpose Y. And you will notice here that I have removed the transpose from here because these two matrices, okay, sorry, this matrix is a symmetric matrix. So it transpose will be equal to the original matrix, and I will prove to you that how this matrix is a symmetric matrix. Okay, I will make a next part of this video to prove this, that it is a symmetric matrix. And now finally we have got our beta matrix, which is equal to beta is equal to X transpose X inverse multiplied by X transpose y. And yeah, we have got our beta, and this beta represents the intercept and the coefficient we require to predict our target variable. So this contains beta 0, beta 1 up to beta m. This is the coefficient of my first column, and this is the coefficient of my mth column. And the shape of this matrix would be of the form m plus 1 multiplied by 1, and this is my intercept, right? So yeah, we have got our beta matrix, which will minimize the loss function. And then we are left with two parts where first I need to prove this, that it is a symmetric matrix. And the other part that I have to prove that these two terms are equal, which is implying that this matrix is a symmetric matrix. Okay, so yeah, we will move ahead in our next part to prove these. Okay, so now we will be proving that this term, yeah, sorry for the delay. This term is equal. We need to prove this, right? Okay, so this is my term y y I transpose x beta minus beta transpose x transpose yi, and I have to prove that these both terms are equal. Okay, so let's say I write it as y transpose y hat is equal to uh, y hat transpose y transpose. Sorry, this is y, right? So if I want to prove this, if I assume my a to be y is equal to a and y transpose is equal to b. Okay, so how I can rewrite this as a transpose y hat is b and y is a. A transpose b is equal to b transpose a. I need to prove this, right? So if I take my first term, a transpose b, and take the whole transpose of it, it will be b transpose a, right? So you will notice that this RHS and this RHS is same. So what I need to prove is that are these two equal same? That is A transpose B is equal to A transpose B whole transpose. This implies, is this matrix a symmetric matrix? Okay. So if I rewrite my terms, that A transpose is Y transpose and B is Y hat, and I need to prove this to be symmetric, right? If I prove this to be symmetric, I can say that uh, my the this point, that where we started, is a symmetric matrix, and if we take the transpose of it, it will be completely transformed to this matrix, and both these will be equal. Okay, so how do I prove this to be a symmetric matrix? So okay, so we were here that we wanted to prove this y transpose y hat to be symmetric, right? So I can rewrite my y transpose y hat as y transpose multiplied by x into beta, right? Because y hat is x multiplied by beta. So the shape of my y transpose is, it is one column or one row multiplied by n number of outputs, right? The shape of my x matrix is, it has n columns multiplied by m plus 1, n rows multiplied by m plus 1 columns. My beta matrix has m plus 1 columns, sorry, m plus 1 rows multiplied by one column, right? So when I multiply x into b, I will get a matrix of n into one shape, right? So the shape will be n into 1. So you will find here that if I multiply this term with this term, I will get a new matrix of shape 1 into 1. That this implies it would be a scalar value, right? It could be 2, 7, anything. It will be a scalar value, and a transpose of a scalar is that scalar itself. This implies we have proved here that my y transpose y hat matrix is a symmetric matrix because the transpose of y transpose y hat O transpose is equal to y transpose y hat. So yeah, we have proved this part that these both terms were equal, and we have followed the path to to find our beta values which are minimized. And one thing is left that I need to prove here. Uh, yeah, this was this proof that this matrix is also a symmetric matrix, right? That's why the transpose could be removed from here to show that beta is this. Okay. Okay, so now we were at the last part where we have to prove this term to be equal to this term, that x transpose x inverse the whole transpose is equal to x transpose x inverse, right? This implies that we want to prove that this term is symmetric. Okay, so let's say our x transpose x is equal to a, right? And if I write it as A multiplied by A inverse, this is equal to I. Okay, right? This is a property. So this is step one. This is step two. Step three is if I take the transpose of this term, A into A inverse whole transpose is equal to I transpose, right? And this implies, uh, okay. So the fourth step implies it will be A inverse transpose multiplied by A, which is equal to I, right? Because I transpose is equal to I. And if I multiply A inverse on both the side, A inverse transpose A inverse is equal to I into A inverse, right? And it will be equal to A inverse transpose I is equals to I into A inverse. And hence can I cancel this I? This is the question. If A inverse transpose I, okay, so of course I won't cancel it. A inverse transpose I is equal to A inverse I transpose, right? And this will be equal to A inverse. So hence we have proved that both our terms were the matrix that we had x transpose x inverse is symmetric, right? So yeah, A, what was A? A was X transpose X, right? So X transpose X whole inverse whole transpose is equal to X transpose X inverse. And this is what we wanted to prove. So now we have proved all the things, and we have our final beta as our beta was, yeah, this is my beta. X transpose X inverse multiplied by X transpose Y. Okay, so now we will be working on this term uh, to figure out what is this and how does this formulation works. And we will build a code on it to which will be similar to what scikit-learn's library OLS model of linear regression have. And we will prove the results that it is exactly same. The math is exactly same. What is working behind that? library and what we have proved till now, right? Yeah. So now let's try to figure out what is this beta matrix, which will be the output of this multiplication, right? So the shape of my X transpose would be M plus 1 into N, right? And shape of X would be N into M plus 1 columns. So if I multiply these both terms, I will get a matrix of M plus 1 comma M plus 1, right? Now, if I multiply X transpose, that is M plus 1 into N with Y, and Y matrix would be of shape, it will be having N rows and one column, right? So the shape of this multiplication would be M plus 1 into 1. Yeah. And when I'm multiplying this, yeah. So this is one matrix and my another matrix is this, right? So when I multiply these terms, I will get the beta, which is of the shape M plus 1 multiplied by 1. So what is this M plus 1 representing? It is representing that I will be having beta 0, beta 1 up to beta M. This is my intercept value. This is my coefficient or the slope corresponding to my first column. This beta 2 is my slope corresponding to my second column. This beta m is the slope of my mth column corresponding to my mth column, right? So yeah, this will be the beta matrix. If I take the first, it will be the intercept. Rest all will be my coefficients, right? And if we break this down further that how will this be working? So if I rewrite this here, beta is equals to X transpose X inverse multiplied by X transpose Y. So what does this represent? So let's say we have uh, two input columns A and B, and this is my C, which is the output column. And if I have terms here 1, 2, 3, 4, 5, 6. Okay, let's say it is representing some CGPA and this is some work experience and this is the placement value, right? And these terms are, let's say, uh, 12, 11, 10. Okay, so what will happen now is that what will be my X matrix? This will be my X matrix. That is my input column. Okay. And when I take transpose of this, it will be 1, 4, um, I'm sorry, 1, 2, 3, 4, 5, 6. And when I multiply it with 1, 4, 2, 5, 3, 6, I will, okay. So the shape of this matrix is 2 into 3, and this is 3 into 2, right? When I multiply this, I will get a matrix of 2 multiplied by 2. Let's say it is this, okay, A, B, C, D, E, F. Sorry, 2 multiplied by 2 it is. So it is the matrix. And if I take the inverse of this matrix, so what is the inverse of A is 1 upon determinant of A multiplied by adjoint of this A matrix, right? So when I take the inverse of this matrix and uh, multiply it with X transpose Y. So this is a 2 cross 2 matrix, which I have received right now. When I multiply it with X transpose, so X transpose is again this uh, 1, 2, 3, 4, 5, 6 in this form. 1, 2, 3, 4, 5, 6. And Y is my output column. So this is my output column, which is this C, right? 12, 11, and 10. 12, 11, and 10. Right, so the shape of this is 2 cross 3 and it is 3 cross 1. So I will get a matrix of 2 cross 1, right? And here I have a 2 cross 2 matrix and my output would be 2 cross 1. Yeah, so we have done an error here. Remember the X matrix, in at X matrix, we add a term 1 here, okay, to which gets multiplied with the beta naught, okay. So this is now my X matrix, and uh, its transpose would also be of the shape 3 cross 3. It will be 1 1 1, and here it is 1 1 1, which is 3 cross 3. So I will be getting this matrix as 3 cross 3, right? And multiply when I take the inverse of this matrix and I multiplied this 3 cross 3 matrix with X transpose Y. So this is exactly same, and this is 2 cross 1, and this must be 3 cross 1, right? Yeah, we have done this correct. And yeah, so this is 1 1 1, this is 3 cross 3, this is 3 cross 1, so it is also a uh 3 cross 3, and this is 3 cross 1 matrix, and this is a 3 cross 1 matrix. When and we are multiplying it with a 3 cross 3 matrix, right? So we will be getting a beta matrix which will be of 3 cross 1, which is 3 rows and 1 column, and this will be beta 0, beta 1, and beta 2. So what does these betas represent? Let's say it has a value 2, it has a value 3, and it has a value 4. So whenever I give a new data point, let's say CGPA and experience, to my function or the model, it will predict the placement value like this. Placement or the LPA package is equal to beta naught plus beta 1 CGPA plus beta 2 into experience. So this is 2 plus 3 times, let's say the CGPA is 8, plus beta 2, which is 4, multiplied by, let's say, experience is 1. Okay, so the new placement predicted amount will be 2 plus 16 plus 4, that is 22 lakhs per annum. So this is how the whole model works. In the next part, we will build this model from scratch, right? So yeah, thank you. Okay, so now in this part of the video, we will try to understand the implementation of the scikit-learn library, and we will build the code through scratch and apply a linear regression model on multiple inputs column, first through scikit-learn and second through our class made from scratch. Okay, so here I have done nothing but generated some random points or data points and created a data frame with two input features and one output column. Okay, so this is my data, and uh, there are no null features in my data, right? And I have imported train test split from Sklearn model selection, and I have split my data into train and test set with a ratio of 0.2 and 20%. 20% of my data is in test set, right? And I have sent my first two columns as input columns here. And this is my last column I have given as the output. Okay, so this is the first five column rows of my training data. And then I have imported linear regression from sklearn, and I have trained the model here. I have passed my train set and input and output of training data. Okay, so and yeah, so then I have predicted my model on the testing set, and these are the first five predictions uh, of my model with respect to the test set. Then the R2 score, which tests the accuracy of my model, and it is coming out to be 95.8%, 95%, right? And the coefficients of my column 1 is 1.95 and the coefficient of my column 2 is 3.31. This is the beta 1 and beta 2 we have discussed. And this is the beta naught which we have discussed. This is the intercept term which is coming out to be 4.58. Okay, so uh, when I implemented this lr.fit, what happened in the backend is that what we have studied all was implemented here. So first, this column was row was generated with each element as one, and x was passed in this formula, and y was also passed here, and which helped me to calculate my beta 0, beta 1, and beta 2, right? So yeah, these are my betas which are calculated after that process. And so now we will try to build this linear regression class from scratch, right? And it is nothing new. We have studied everything. We just need to convert it into a code, right? So uh, the basic first thing which I need to predict anything is my value of beta matrix. I need the coefficients and I need the interceptor. And to calculate it, I have this formula, x transpose x whole inverse x transpose y, right? So here I have created my class linear reg, and I have said that set the beta to none for now. And when I call my fit function L linear regression dot fit, it will take two inputs from me. It is the training data, the input columns and the output column, right? Target column. And then what internally it will do, it will set the first column. It will assign the value 1 to my first column, right? So it is here written in the code, column stack np.1's length. I need ones of the length of my training data, right? So if the length of my training data is 10 rows, so I need 10 ones right here. So it is written there. Yeah. Then after, what it is doing is it is applying this formula. It is applying this formula. So first I have the dot product. First I have the dot product of my x train transpose and x train, which is this, and then its inverse. So this is the function we can call for inversing a matrix, right? np dot linear algebra dot inverse. Then after, what I am doing is that I am taking these two matrices, X train transpose and Y train, and doing a dot product of them. So this will give me two new matrices, upon which when I apply dot product, I will get this beta, get this uh, beta matrix, which is of the shape 3, yeah, 3 cross 1. This will be the matrix I will get, in which the first element will be the beta naught, second will be the beta 1, and third will be the beta 2, right? Okay, so yeah, so this is the formula which I have applied here, np dot and this, and okay, so let's print it. Okay, so now if I implement this code, I make L as my linear regression, and call L dot fit X train and Y train. So what is giving me? It is printing this beta matrix, which is first element is my coefficient. Uh, uh, First element is my intercept, and the second and third one are my coefficients, right? And yeah. Yeah, so you can compare these terms with the scikit-learn libraries coefficients which it has calculated, and you will notice that it is exactly same. So intercept is 4.58, and yeah, this is the intercept 4.58. The coefficients are 1.95 and 3.31. 1.95 and 3.31, and you can see these are exactly same outputs as we compare it to the Sklearn library, right? So now I want to predict when someone give me a query when with two input points, and I want to predict the output. So what will happen is that I will get a X test, right? This is the testing data frame. I will show you what is X test. So these are the input features. See, you will notice I don't have the output feature here. And when I give these input points to my predict function, what it will do is first it will create a vector, a series of one and stack it here. So it will again make this two input columns into three input columns, where this first column will be containing all the ones, right? And yeah, simply now I need to just dot product my uh, X test with the beta coefficients, which is this. Okay, I will show you. Hmm, this is the loss function. Yeah, this is the output. We have calculated the target will be X into dot product of beta matrix. And this will give me a output of n into one number. The shape of this Y matrix will be n into one. That n number of rows for each input column, input row, and it will be a one column, right? So yeah, and we can call the predict function and pass in the testing data and pass our testing data, and these are the predictions. Uh, and yeah, you can check the R2 score. It is also exactly same R2 score which we calculated for our by our sklearn library, right? So yeah, this was the implementation, and we built the code from scratch of linear regression, and this is the OLS, ordinary least square version of linear regression. In the next sessions, we will look for different methods of applying linear regression and see what are the limitations of OLS and what are its advantages and disadvantages, right? So thank you for watching.